up quite nicely once you find the least common denominator. So now you can find critical numbers by setting this equal to 0. The function is undefined at 0, so is its derivative. So there is no discussion there. There is no critical numbers coming from f prime being undefined where the function is defined. So only when I set this equal to 0. And I get 6x squared plus x minus 2 equals 0, which has two real solutions. Very good problem overall. Is this better? Okay, anything else? Is there anything else you tried? Anything else you want to look at? Okay, so then can I continue with 4.2? Okay. 4.2 deals with two theorems. Rawls theorem and later on the mean value theorem. So for now on, for the moment, let's talk about Rawls theorem. So let's take a look at the following scenario. No, I'm not going to graph our best friend. There is something else, finally. Here's a function. Here's a function between a and b. If I say or write that f of x, number one, f of x continuous on the closed interval a comma b, and f of x differentiable on the interval a comma b. It may have a vertical tangent here, so I don't know. At the endpoints, I don't care. Would you agree with these two statements? Is this function continuous on AB? Does it have a unique tangent at any point between A and B? And not a vertical tangent between A and B? Okay, if you agree with that, I'm hoping that you're going to agree with a third condition or hypothesis. The third hypothesis says that f of A equals f of B. That's exactly how I started the graph, right? I drew a horizontal line, and I pictured the graph. I drew a graph between A and B that starts at the same point, the same height as it ends. Okay, now can I graph some other function? It's another option. Can I graph another option? Yes, but I don't want to just put too many options in there. You will see in a minute why I graph the other option. So you agree that it doesn't matter if it's the pink or the other graph. F of x in both cases is continuous between a and b and is differentiable between a and b. And it starts at the same point as it ends when it comes to the y-axis, the y value. Perfect. So therefore, by the Rawls theorem, there exists a C in the open interval a comma b such that, and I should say here at least, so there exists at least one C between A and B such that, now let's analyze, such that what? So let's look at the pink for now, the pink graph. Such as what? Such as? Thank you very much. Exactly. Such that f prime of c is 0. And now let's look at the other option, because I graphed two functions between the same points. So here's a c1, here is a c2, here's a c3, and so on and so forth. So Rolle's theorem, if the three hypotheses are fulfilled, it guarantees at least one turning point, we say, where the derivative is 0, of course. It guarantees at least one turning point. So if those three conditions are fulfilled, continuous, differentiable, and f of a equals f of b, Rolle's theorem guarantees at least one turning point. It can have many. It can have as many as you want. In this graph, I have 1. Here, I have 3, where the derivative is 0. In other words, what we're interested in to say is that there is a turning point. There is a max or a min. The function attains a max or a min point, a point of maxima. Let's look at a problem. On page 288, let's look at number 3. We have f of x equals the square root of x minus, I think it's 1/3. Is it 1/3? And the interval is given to us 0 to 9. So we're given a function, and the question is asking us to verify that the function satisfies the three hypotheses of Rolle's theorem on the given interval. Then find all numbers c that satisfy the conclusion of Rolle's theorem. Are you okay? Yeah. Perfect. So we start by looking at number 1. Is this function continuous on 0, 9? This is continuous everywhere. And this is continuous on 0, 9 because we imagine the graph. As at x equals 0 is 0, and at 9 is 3. So it's a piece of the graph between 0 and 9. It's a radical function. It's continuous everywhere on its domain, and 0, 9 is in its domain. So is that satisfied? Part B, or 2, f differentiable on the open interval 0, 9. Do we agree with that? This is differentiable everywhere, and this is differentiable everywhere except at 0. But 0 is not there. We know the graph. It has a vertical tangent at 0, but we're not interested in the endpoints. That's why we have an open interval. And now, if the third condition is not fulfilled, then we'll say, sorry, Rolle's theorem does not apply. So I have to find f of 0, and I have to find f of 9. If these two are not the same and not equal, then I'll say, sorry, Rolle's theorem is not applicable. So at 0 is 0. And what about at 9? Yes? Is it? Good. So now, Rolle's theorem does not tell us where is the maximum, but it says for sure there exists at least a c in the open interval 0, 9 such that f prime of c is 0. Now we can determine it. So solving this equation, we will get c. So Rolle's theorem says there must be at least one. Now find it. So we differentiate f of x, and we get f prime of x and I get 1 over 2 the square root of x minus 1/3. Would you agree with that? So now in order to create this equation, I will have to replace, it doesn't really matter if you don't, but let's replace x by c. So 1 over 2 the square root of c minus 1/3 equals 0. And yes, now I have to determine c from this equation. So 1 over 2 the square root of c equals 1 over 3. I moved 1/3 to the other side. And you can cross multiply, which I hope you would say. Or you can say two fractions are equal, okay, but if they also have the numerators equal, the denominators must be the same, or you simply cross multiply. So then 2 the square root of c must equal 3. So if two fractions are equal and they have the same numerator, they must have the same denominator, otherwise they will not be equal. So we will divide both sides by 2. We get the square root of c equals 3/2. And now we square both sides and we get c equals 9/4. Now I have to make sure that this is in the interval 0, 9. And of course it is, right? It's a little bit more than 2. So in this particular case, the function has only one c, where it has a max or a min. So this is the critical number. And we don't know if it has a max or a min. That part the Rolle's theorem does not help us with. But we can study the sign and we'll determine whether this is a max or a min. If it changes from positive to negative, it's a max. If it changes, the sign of the derivative changes from negative to positive, then it's a min. Any questions on this? So that's guaranteed by the mean value, by the Rolle's theorem. And now the mean value theorem. Are we in the clear with this? Okay. So one more theorem is very similar at the beginning anyway. It's called the mean value theorem. It starts like Rolle's theorem. But let me show you a picture so we see what we understand what's happening here. This time, there is no requirement for f of a and f of b to be the same. So this is point A. Let's say this is point B. And the function does this. So this is f of x. It's very clear that f of a and f of b are not the same. Would you agree? Perfect. So obviously, number 1 and number 2 are identical with Rolle's theorem. In number 1, we know that f is continuous on a comma b. Here it is. This is a, and this is b. So on the closed interval a comma b, the function is continuous. Now, f is also differentiable on the open interval a comma b. Would you agree? The third hypothesis is not there anymore. They don't have to be at the same height, same y value. So please pay attention for a moment. Okay, so imagine that I draw this line. Can anyone give us the slope of this line? And you can say, I have no idea what you're talking about because you didn't put all these coordinates. That's fine. So this is b, f of b, and this is a, f of a, f of a. So now you can give me the slope of the line segment AB. What is it? Minus f of a over. Very good. No difficulty there. So please pay attention to what I'm going to do next. I'm going to do this. Imagine that I draw parallel lines with the line segment A comma B, and I stop with a tangent. Can you help me? Thank you, because I don't want to move my hand. Thank you very much. Okay. Okay, can anyone give us the slope of the tangent line at point C? F prime of C. Now, can anyone tell us the relationship between this and this? Because you saw what I did. Exactly. Because the two lines are parallel. So they have to be the same. So then F prime of C must equal F of B minus F of A over B minus A. So, by the mean value theorem, MVT, there exists at least, because I can continue like we just did, there exists at least a C in the open interval A comma B such that F prime of C equals F of B minus F of A over B minus A. Ready for an example? Okay, on page 289. Let's look at 11. We're given a function, natural log x. We're given the interval 1 comma 4. Verify that the function satisfies the hypothesis of the mean value theorem on the given interval. Then find all numbers C that satisfy the conclusion of the mean value theorem. Where is the starting point here? What do I have to write? Remembering the graph of this function, I know that what? I know that, number one, f of x is continuous on the interval 1 comma 4. Do I know that? I do, because here's the graph. And this is 1, and this is 4. So the function is definitely continuous on the interval 1 comma 4. Number 2, is f of x differentiable on at least the open interval 1 comma 4? Perfect. Then it's guaranteed by MVT, at least a C, in the open interval 1 comma 4, such that what? Prime of C equals, so now we plug in the numbers. F of 4 minus, very good, over, that's it. So that's guaranteed by the theorem, by MVT, by the mean value theorem. But now we have to determine C. So first, on the left-hand side, I have the derivative of natural log, which is 1 over x, but since I have C, I'm going to write 1 over C. Now, f of 4 is just natural log 4. What about f of 1? 0 divided by 4 minus 1, which is 3. 4 minus 1 is 3. F of 1 is 0. Natural log 4 is, f of 4 is natural log 4. This is a proportion. I'm solving for C. In a proportion, I'm allowed to do this trick, as long as I swap, I reverse both. So C equals 3 divided by natural log 4. This better be between 1 and 4. If it's not between 1 and 4, then we have an error somewhere. So let's give it a shot. Where is it? Here it is. Okay, so natural log, I'm sorry, 3 over natural log 4. And this better be between 1 and 4. And it is. It's 2.164. Any questions? Okay, I would like to look at an application of this. So let's read problem 24. Suppose that f prime of x is between 3 and 5 for all values of x. Show that 18 is less than or equal to this, less than or equal to 30. So let's copy what we have. So this is 24 on page 289. So we are told that f prime of x is between 3 and 5 for all x. All x. They're asking us to show something like this. Okay, so we have to get to this. We don't have this. They're asking us to, but we have some information given here in the question. All I know about this f prime of x for all x is that f of b minus f of a divided by b minus a for anything must be between 3 and 5. How did I come up with that? Well, from Rolle's theorem, we have to assume that this function is continuous and differentiable. And f prime is somewhere between 3 and 5 everywhere. So then I used the mean value theorem, writing f of b minus f of a over b minus a. Now the question is, what is b and what is a? By comparison, of course, I will figure out that a is good and b must be indeed. So let's see what happens. So then 3 less than or equal to f of 8 minus f of 2 divided by 8 minus 2 is less than or equal to 5. Or 3 less than or equal to f of 8 minus f of 2 over 6 is less than or equal to 5. And what is my final step? Yes, because that's what I want in the middle. Very good. Thank you. So then this is 18 less than or equal to f of 8 minus f of 2 less than or equal to 30. And that's exactly what we wanted to show. So that's one of the multiple applications of the mean value theorem. Questions? Questions? Is this okay? Okay. So last time we went beyond basically 4.1 by discussing, and I want to refresh your memory on that, about the first derivative test. For that three. First derivative test, and then we'll look at the second derivative test as well. The first derivative test says that if a function f of x has a critical number at x equals c, and f prime of c changes sign, or the derivative, I would say better, f prime of x changes sign at c, either from plus to negative, which is a max, or from negative to positive, which is a min, or it does not change sign, no max min. So that's in plain English what the first derivative test says. So if the function has a critical number, if f of x has a critical number at x equals c, and the first derivative changes sign from positive to negative, or from negative to positive, there is a max and a min respectively, but if it does not change, no max min. Also, it has a critical number coming from f prime being 0 or from f prime being undefined. It doesn't matter. So if it's a critical number, and if the derivative, the first derivative changes sign, and it changes sign from positive to negative, it has a maximum. It can be local or absolute, we don't know, but at least a maximum for sure, relative, or local, or from negative to positive, there is a minimum. That's the first derivative test. We already applied it last time. And before we look at a function, I would like to discuss what happens when we look at the second derivative. Not the second derivative test just yet. Let's say what the second derivative gives about the function. So second derivative. Not the second derivative test yet. So we know that if the first derivative is positive, the function does what again? Very good. If the first derivative is less than 0, what does the function do? Decrease. Very good. But now let's analyze what happens when we study the second derivative. And when we set the second derivative equal to 0. This is still not the second derivative test. We're still discussing. Okay, if the second derivative of a function is positive, the function, we say it holds water. It's concave up, upward. If the second derivative is negative, the function is concave down. What happens when the second derivative is 0 and it changes sign from positive to negative or from negative to positive? It's the same answer this time. What will that be? What will happen at that point where the second derivative is 0 and the function is defined? Second derivative is 0 and it changes sign. What will that be? If you remember, you don't have to. That is called it changes concavity from opening upward to opening downward, or vice versa, from opening downward to opening upward. So an inflection point exists when the function is defined, when the second derivative is 0, and the second derivative changes sign. So here are situations from opening downward to opening upward. The point of inflection is right here. Or from opening upward to opening downward. The point of inflection is here. So at that point, number 1, the function is defined. Number 2, the second derivative is 0. And number 3, the second derivative changes sign. It doesn't matter. I mean, it does matter if it's from negative to positive or from positive to negative, but it does not have two different situations like with a sequence of signs. It does because it's, but you know what I mean. Okay, now I personally almost never use the second derivative test, but I would like you to know what it means. Before we look at the second derivative test, because it's easier to work on an example, let's pick an example, go through everything, graph the function, and then I'll explain on that particular example, I will explain what the second derivative test does. And you're more than welcome to use it if you like to, if you feel that it's a better option. Okay, so here it is, a problem, or several problems, on page 298. Let's take a look. I'd like us to choose from here. Page 298. Find the intervals on which the function is increasing, decreasing. Oops, no one can see. Find the local max, local min, and find the intervals of concavity. They are called intervals of concavity, and the inflection points. In this particular case, we're not asked to graph. I would like to go ahead and do the whole thing with the graph, but it doesn't matter. Any preference? Which one? 17, this one? Okay, very good. X squared minus x minus natural log x. So 17 on page 298, f of x. One more time, I think I saw everything correctly, yes. Perfect. I get my table going from the very beginning. F prime is first, f of x in the middle, and last one now, and the table is complete. I promise I will not add anything else to it. This is it. Now, let me show you what the book does. If you prefer this method, I'm more than happy to see that, how you apply it. This doesn't help me at all. And I'll show you how we already done this several times last time. I don't recommend this. But if you understand it, it's fine. Another table that I definitely don't recommend is something like not even a table. There is nothing. There is no summary. And if you ask me how they came up with this, I'll have no clue. I'll have to start from scratch and work on the function. There is no explanation. And finally, they have this table again, which doesn't mean anything. So again, if you read and you understand that and you're happy with it, I'm happy with it. I will never use it myself, though, because I can't explain anything. Okay. So we're asked a lot of things about this function. However, the first step must be only one, and that is like with any function. There's one step that has to be the first, always. Excellent. What is the domain of this function? Careful. Careful. Imagine the graph of natural log. Where does it start? 0. Very good. 0 to infinity is the domain of this function. Excellent. That's the starting point. Thank you. Well done. Good. So now I will find the derivative, set it equal to 0, and take it from there. Because I want to graph it, I will also determine the limits and the x and y intercepts, if they exist. But in a minute. So let's start with f prime. So this is 2x minus 1 over x. Do you agree? And then you will agree with 2x squared minus x minus 1 over x. And obviously, we have to draw this. If the function is not defined at 0, its derivatives will not be defined at 0 for sure. Luckily for us, the numerator is factorable. How do I factor the numerator? Because I need to set it equal to 0. I agree. 2x squared minus 2x and plus x and minus 1. Very good. So this is 0, and we will get 2 intercepts. And you can say not so fast. We'll get x equals negative 1/2, but it's not in the domain, so you cannot even put it in the table. And the second one will be x equals 1, which I can put in the table, and it will be 0. I didn't mean that. I meant this. And it happens that when I plug in 1, I jumped ahead. So it's 1 minus 1, which is 0, and this is 0. So it happens that that is 0 as well. Okay, now I have to study the sign of the derivative, left and right. To the left-hand side of 1, let's say at 0.5. This is positive, but 0.5 minus 1 is negative. So this is negative. So what about at 10? This is positive, this is positive, this is positive. So now, what will you say? We haven't finished. We're not even halfway through. But what will you say about the interval 0, 1? What does the function do on the interval 0, 1? We haven't checked. We haven't put the information for the function yet. But by simply looking at the first derivative, what will you say the function is doing between 0 and 1? The function is decreasing. What will you say the function is doing between 1 and infinity? The function is increasing. But again, we haven't finished. So let's determine now this limit. I need to determine this limit, and I need to determine this limit. Ready? Okay, so let's write limit as x approaches 0 from the right of the function. Limit as x approaches 0 from the right of x squared minus x minus natural log x. Where does this go when x approaches 0? Perfect. Where does this go when x approaches 0? Perfect. Where does this go when x approaches 0? Without the sign for a moment. Imagine the graph. But there is a minus in front of it. Yes. So the answer is infinity. So I go back to my table and put infinity where it belongs. Now I want this limit. So limit as x approaches infinity from x squared minus x minus natural log. Okay, where does this go? Where does this go? Okay, but this one is bigger. Would you agree? Because this is squared. So I can disregard this for a moment. Where does this go? Infinity, with minus in front. Right. But again, which one is bigger? Is this bigger than this? This is infinity squared. And this is minus infinity minus infinity. Which one of these will dictate? This one. So it is infinity. Okay. So from infinity to 0, what does the function do? It decreases, and it's supported. That is supported by the sign of the first derivative. Now is the moment of truth when I make sure that these two cooperate. From 0 to infinity, the function is increasing. Agreed? Perfect. So let's look at the second derivative. Oh, by the way, what is 1 comma 0? 1 comma 0. Negative, 0, positive. Yes, local min. It could be global, but at least for sure it's local. Now let's look at the second derivative. This is what I want to differentiate. Not this and not this. I want this. So f prime equals 2x minus 1 over x. So let's differentiate and get the second derivative. Can anyone help with the second derivative? Obviously 2. This is 0. But when we differentiate, remember some time ago I said, please remember that 1 over x prime is negative. Yes, with minus in front. So plus 1 over x squared. So now this becomes 2x squared plus 1 divided by x squared. And yes, I want to set this equal to 0, but what do you think? Because I'm trying to find concavity, and I'm trying to find the intervals of concavity, and I'm trying to find deflection points. But what can you say about this? Forever. Always. It's what? It's exactly. So there is no discussion there. There's nothing I can do. And the function, it's opening up. So there are no inflection points. The function is all the time concave upward. And now, this is a perfect example in which we want to discuss. Do not erase anything. I'll put them back in. This is a perfect example in which we want to discuss the second derivative test. Don't erase anything. And then I'll explain why I'm not using it. Imagine that we determined the critical number. The critical number was 1, and the first derivative was 0 at that point. And now imagine that we don't want to study the sign of the first derivative. For whatever reason, we decided not to, which in my opinion is a mistake, because that's when I catch my mistakes. If these two rows don't cooperate, then I know, oops, there is some error. But the second derivative test says this. You don't have to determine the sign of the first derivative. And then you will figure it out, here is how. But it's already too late. If I made a mistake with the first derivative, then I have a mistake with the second derivative. So it says this. if you find the second derivative and the second derivative opens up, like in this case, all the time, it does not have an inflection point, what kind of point can 1 comma 0 be? It must be a minimum. Therefore, the signs of the first derivative must be these. So that's the second derivative test. It says this. If there is a critical number, and now I jump to the second derivative, and the second derivative is positive, that must be a minimum. If there is a critical number, and the second derivative is negative, there must be a max. That's the second derivative test. And you understand why I'm not using it. Because that's how I check myself. That's how I know whether these two are in sync. Because if they're not in sync, then the second derivative, I may already have a mistake in the first derivative, and I carry it over to the second derivative, and then. So let's write the second derivative. Let's finish up with the graph, and then we'll write the second derivative test. So here's the graph. It's only between 0 and infinity. The function has a vertical asymptote at 0. And 1 comma 0, it opens upward. And this is the graph of x squared minus x minus natural log x. I was going to write the derivative. I don't know why. Any questions?
Does it follow this pattern for more derivatives?
Say it again. No, this is it. This is it. The first derivative will tell us increasing, decreasing, and max min. The second derivative will tell us concavity, upwards and downward, and the inflection point. Yeah. Now, if I'm interested in studying the second derivative and graph the second derivative, then I have to go to the third and the fourth. Bless you. But if I'm interested in the function itself, no. So, of course, I don't care for negative numbers, so from 0 to 10, and from a negative 2 to positive 10. So here's the graph. Oh, we know that the graphing calculator is lying. The function does not start here. It goes all the way to infinity. It has a turn or an x-intercept, in other words, and a critical number. And this is the absolute min, not just the local min. So this is the absolute min of the function. The range is 0 to infinity. So we already know a lot of information about this. So this is at 1. So that's how we put together the first derivative with the second derivative, and then and the limits, of course, and then we are ready to graph the function. So the second derivative test. The second derivative test says this: if C is a critical number and f double prime of C is positive, C gives a minimum. Number 2, if C is a critical number and f double prime is less than 0, C gives a max. I don't particularly like it, and I told you why. I mean, I like it. I don't have anything against it, but I don't use it. I would like us to practice more. So we can choose another function. I also would like us to choose to graph an example of a function with all this information. I would like to look at a word problem with reading from the information we are given in the graph. I would like us to choose maybe even from here, in which we are trying to determine everything. Again, concavity, max, min, etc., etc. So please choose, or I will. Do you want to start with an example of a function, given the conditions? Or you would like to go back to a graph in which we determine everything? We couldn't do this in pre-calculus, right? Because we didn't have derivatives, we couldn't determine inflection points, we couldn't determine max without a calculator, but now we can determine everything. We do have some limitations depending on how difficult the function is, but now we can determine everything. So would we like to start with or continue with given conditions, summarize the conditions, and come up with a graph? Number 26 it is. Let's copy it. 26. 26 on 298. It will take me a couple of minutes to copy all the conditions, but that's what it is. So 26. 298. So we have f prime of 1 equals f prime of -1 and equals 0. F prime of x less than 0 if the absolute value of x is less than 1. F prime of x is greater than 0 if the absolute value of x is between 1 and 2. F prime of x is -1 if the absolute value of x is greater than 2. The second derivative is less than 0 if x is between -2 and 0. And they say inflection point, IP, inflection point at 0, 1.